Okay, so I will give you midterm 2 on Friday, and again, unless you tell me otherwise, only your top midterm counts. Okay, plus you. I'll risk it. How many of you remember the integral test from calculus?
I remember it, you said it.
Do you remember it's unique?
The same name.
The integral test. So the idea behind the integral test is to estimate the value of a series. The way you've seen it in calculus might have been just to evaluate whether or not a series converges or diverges. But of course, if you can bound something above and below, you can estimate it. And so the more refined you make it, the more careful the analysis, the better estimate you can have for the actual value of the series. So the general framework is the following. You have a sequence an of, say, non-negative terms, either non-decreasing or non-increasing. Right. So the sequence is either never getting smaller or never getting larger as you walk down, one or the other. And let's say you have an is less equal to fn for some non-decreasing function. And of course, you could have something very similar for a decreasing sequence. Then the sum of an converges if and only if the integral of f of x dx converges. And you can estimate the sum by the integral. So I'm not going to prove the integral test. I'm going to basically just go through the integral test for the special case of the Stirling's formula of n factorial. And it'll be a pretty good approximation. And we'll talk about how we could have made it a better approximation. The hardest part in the integral test is trying to figure out what function to take. The typical rule is whenever you see the letter n, replace it with the letter. So I have to replace it with the letter x. Most of the time that will work. Okay? There's a few times you might have trouble. If I give you n factorial, okay, I could replace it with x, but then what does x factorial mean? Well, fortunately, we're now beyond Calc 3, and we've seen the gamma function. All right, so let's do an example. The integral test and Stirling. So we talked a little bit about how we should attack this last time. And what's our Pavlovian response when we see n factorial? What do we want to do to it?
Log.
We want to take a log of it. Right? Because we take a log, this is now the log of 1 plus the log of 2 plus the log of n. And this should look a lot like an integral. And so what I'm going to do is I'm going to just sketch it a little carefully. So here's 0, here's 1, 2, 3, n minus 1, and n plus 1. I'm going to be a little careless just in the interest of time. If you want to do it more carefully, I strongly urge you to do so. You can also check the book. You can also check the source of all wisdom, which is... Ooh. I would probably put Wolfram Alpha second. Wikipedia. Yeah, Wikipedia has a really nice, I think, description of how this is done. Wikipedia math is pretty good, and it's pretty stable. Unlike Wikipedia politics, which is a function of who was the last person to upload. But Wikipedia math is very stable. So let's plot what the log of 1 plus the log of 2 plus the log of 3 plus dot 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 plus log of n looks like. So I'm going to draw my function from 1 to 2, which would be log of 1. And then from 2 to 3 will be log of 2. And then from 3 to 4 will be log of 3. And then from n to n plus 1, this will be the height of log n. That's log 1, log 2, log 3. What's nice is because each of these has width of 1, The area of each rectangle is just log 1 plus log 2 plus log 3. That's exactly my sum. So to calculate the sum, I just need to find the area of these rectangles. So there's two things I could do. I could take a function that's always a little bit larger, and that would overestimate, and I could take a function that's always a little bit smaller, and that would underestimate. So if I try to take, and then, well, I just crunch this one down a little bit so the log doesn't go nearly as fast as I feel. If I do something like that, the function log x is always just a little bit above. And the reason is at 1, the log of 1 is the same as, not surprisingly, the log of 1, but at the very end of the interval I'm up to log of 2, and it's only still log of 1 here. So the log of x is above this. So if I just find the area under log of x, that's going to be a really good approximation. If I want to underestimate it, what I could do is I could shift all of these units over to the left. And if I were to do it that way, here's 0, here's 1, here's 2, here's 3, here's n minus 1, here's n. And now I draw the log of 1 this way, to the left. And I draw the log of 2 this way. And the log of 3 this way. And now if I took the function log of x, log of x will be below. And I will underestimate. What's the only issue I have with using the log of x to underestimate? So I have to be careful about one small thing.
Log of 0.
Yeah, the log of 0 is negative infinity. Yes, that will help me underestimate, but I really do not want to underestimate by minus infinity. Okay? That's, not nearly good enough. Okay? So, well, let's see. What's the area of this rectangle?
0.
So I don't really have to worry going from 0 to 1. Okay? So when you draw pictures like this, for here, I would just go from 1 all the way up to n. And then this would give me an underestimate. So the integral from 1 to n of log of x dx is less than or equal to the sum, k goes from 1 to n, of log of k is less than or equal to the integral from 1 to n plus 1 log of x dx. So this will give me a really good bound. There are things we can do to evaluate this a little bit better and to think about what is our error, how much are we missing by. But this will give us a pretty good approximation. So now we need to know what function has derivative log of x. Does anybody remember? I know at least one person in this class has seen the function that's the derivative of log of x. That was a few years ago. So what function has derivative log of x?
X log of x plus x.
Almost.
Oh, so the log of base 10.
No, a log is always
X,
basic.
Yeah, never mind. X.
Almost. If you combine the two of your answers, so drop your plus sign and take her minus sign.
Oh,
X log x minus x.
x.
It's
Yeah.
x log x minus x. So here's the idea. We want to try to find a function whose derivative is log of x. It's not going to just be log of x or log of x squared. If I take x log x, what's the derivative of x log x? The derivative of x is 1, and that gives me log of x, which is really good. But then unfortunately I have x times the derivative of log of x. So I get
Yes.
log of x plus 1. Okay, so my guess was close. I have to correct. What function has derivative 1? X. So if I look at x log x minus x, its derivative will be log of x. So again, this is the method of divine inspiration. It's an extremely powerful method. We will be seeing it again when we get to generating functions. And we will also see ways to avoid divine inspiration. Okay? If you have an idea of what the answer is, you can sometimes make a guess and then correct your guess. I'm not expecting to see many hands. I know it's going to be sad, but how many of you have taken differential equations here? Okay. It's actually too high than I was expecting. Have you remember variation of parameters? You get. Did you see variation of parameters? Okay. Did you take the class together?
I took it in physics.
Okay.
I didn't. I took math one.
Okay, then at least your answers can be different without having issues. Variation of parameters is often when you're trying to solve a differential equation. If you guess what the solution is, and you put in some kind of constant function, some kind of function times something that's known, you can often then try to fix your guess. And it gives you, another related differential equation to solve. So it's very similar to what we're doing here. We're guessing the antiderivatives of the form x log x, and then we're trying to correct it. Well, now that we know that, we can calculate the area. Alright, well, the integral of this is just going to be x log x minus x at 1 and n, and this would be x log x minus x at 1 and n plus 1. I'm only going to really work on this one, because this is a little bit easier. The n plus 1 is a pain. Right? If I put in n, I get n log n minus n. Now, I'm just trying to find an upper bound. I can make my life a little bit easier. If I want to look at this integral is almost the same as this integral. What does it differ by? What's the only difference between this integral and this integral? I'm sorry?
The limits of integration.
Yeah. So this integral is the same as this integral, and then integrate from n to n plus 1. So this over here would be n log n minus n plus the integral from n to n plus 1 of the log of x dx. And again, I'm just trying to find an upper bound. Does the function log of x change that much from n to n plus 1? No. So this is approximately, and again, I can just use this as an upper bound, n log n minus n plus the log of n plus 1. And I have the log of n factorial over here, and I have n log n minus n. So in terms of how much they differ by, they don't differ by that much. Alright, I don't think anybody was trying to calculate the log of n factorial. We wanted n factorial. So we exponentiate, and we get e to the n log n minus n. I'll do it slowly. E to the n log n, e to the minus n, is less than or equal to n factorial, is less than or equal to e to the n log n, e to the negative n, e to the log of n plus 1. Alright, what's e to the n log n? You can either get it by doing the algebra or knowing what Stirling's formula is.
N to the n.
It's what?
N to the n.
N to the n. Right? We're supposed to be getting n to the n, e to the minus n. So this piece better be n to the n. The other way to look at it is, this is e to the log n to the nth power. What's e to the log n? I'm raising e by the number of powers of e I need to get n. So e to the log n is just n. So I get n to the n, e to the minus n, less than equal to n factorial, less than equal to n to the n, e to the minus n, and then this is just an n plus 1. Alright, so who remembers what Stirling says? What are we supposed to be getting for n factorial? Yes?
Isn't that root 2 pi n?
It's root 2. That's the square root of 2 pi n. Let's look at the lower and the upper bound. What's the lower bound here? 1. The upper bound here is n. What number's between 1 and n? A lot of numbers, but there's a number that I really like that's between 1 and n. That in some sense is the average of the two numbers. So n over 2 is the arithmetic average. If I add the two numbers, the arithmetic average is n halves. There's another average I could do.
Root n.
I can do the geometric average. So the geometric average of two numbers is you multiply them and take the square root. Well, what's the square root of 1 times n? Which is, so we're off by a factor of square root of 2 pi now. So if we basically say that the error is halfway between these two, why this? Well, if you go back a few steps, if you look at what we have over here, if you take half the error would be 1/2 log n plus 1. A half of the log of n plus 1 is the log of the square root of n plus 1. And then that will exponentiate to the square root of n. So if you basically say, look, I assume that this is roughly halfway between these two. In terms of how my error is being done, you get the square root of n. You're not going to get the constant square root of 2 pi, but you get extremely close. And so, you can make this a little bit more exact, you can make it a little bit more precise. There's a beautiful theory called Euler-Maclaurin summation, which allows you to really isolate what the error terms are here. And so if you want to get a better proof of Stirling, this would be one way to do it. Okay? So again, it's a really nice consequence of the integral test. Yes?
When we evaluate x log x minus x, why don't we get a minus 1?
We do. That's why. So yes, there technically should be, you're right, there should technically be a minus 1 on both of these. Actually, it will become a plus 1, I think.
But then if it's on both sides or all of them?
That's fine, it's on both sides, so we have to bump this up by a little bit by the plus 1. So excellent point. Email me and remember to take M&Ms. So if we put in the 1 over here, we get 1 log 1, which is 0, but we also get a minus 1, and since it's the lower bound, the minus 1 becomes a plus 1. So we have a plus 1 here, we have a plus 1 here, we have a plus 1 there, we have a plus 1 here. I feel sorry for the people watching this on the video. Now we have an E over here, and we would have an E over here. Okay. So now, I'm a little bit worried. What's the, yes?
Oh, no, sorry.
What's the square root of 2 pi? Pi is a little bit over 3, so 2 times pi is about 6.28.
So like 2.5-ish. Less, some number less
So that is just a little bit less than e.
yeah.
So that's a small problem. So then the question is, did we draw our curves the wrong way? Oh wait, that's fine, because this is a lower... this is the lower bound. 1, 2, 3, 4.
Well, yeah, because the lower bound doesn't have the factor of n in it, so it's okay.
Okay, the lower bound doesn't have the
Yeah.
factor of n. Perfect, good. Well, I was about to say, I'm pretty sure Stirling's formula is right. Okay, good. Good. The lower bound doesn't have the factor of n, so we're fine. That would be very bad. I read a story when I was young about a mathematician who actually proves that all of math is inconsistent and just happens to give the right answers to the engineering questions of the world, but there's a fundamental inconsistency, and she goes mad and takes several people with her. But fortunately, Stirling is okay. It would be very bad to lose Stirling's formula. Okay, so we have two things to do now. We can do Stirling and the CLT, or the CLT and Stirling. Any preferences? Which do people want to see first?
CLT and Stirling.
CLT and Stirling. Okay, good choice. Opposite order of what I wrote. Okay. All right. So we're doing CLT and Stirling. So recall, Stirling is n factorial is about n to the n, e to the minus n, square root of 2 pi n. And CLT is x1, xn, iid, v with mean mu, variance sigma squared, finite higher moments, then x1 plus xn is approximately normally distributed with mean n mu and variance n sigma squared. Okay? So the central limit theorem holds for any choice of x1 through xn that are identically distributed that are nice. You can weaken these conditions greatly. Alright, so the first thing is, what is a good choice for the xi's? Do you know anything that kind of looks like it has a something to the n and e to the minus something? Any random variables that we've seen that look like that? We've seen a discrete random variable that looks something like this. Has a parameter lambda. So what have we seen that looks like this?
Poisson.
Poisson. So Poisson with parameter n, and the probability that x equals k is lambda to the k e to the minus lambda over k factorial. So this is something we haven't done yet. But what do you think would happen if I summed two Poissons? If life were good, what would we get? A Poisson. And there's only one possible Poisson we could get. So remember, the mean of a Poisson is its parameter lambda. So the mean of this is lambda 1, the mean of this is lambda 2, the mean of the sum is the sum of the means. So if this is going to be a Poisson, there's only one candidate. What's the candidate? Lambda 1 plus lambda 2. So we're going to prove that now. And then we're going to, I should turn this. So we're going to prove this now. And then once we prove that the sum of two Poissons is a Poisson, then we can try to use the central limit theorem to actually prove Stirling. What we'll do is we'll have x1 through xn will be Poisson random variables with parameter 1. Then the sum of these will be a Poisson with parameter n. And then we know an exact closed form expression for a Poisson random variable with parameter n. But by the central limit theorem, we know it's approximately a Gaussian. And then we can use that to estimate n factorial. So that's the whole idea. Now, of course, then we're going to have to use a theorem we haven't proved yet. So we're going to prove Stirling's formula by using the central limit theorem, which we haven't proved. So the proof of the central limit theorem is not beyond the scope of this class, but it would eat up the entire rest of the semester to do a proof. So what I will do is I will show you a proof under reasonable conditions, assuming 1 or 2 black box results from complex analysis. And then I will try to make sure I prove it in complex analysis, this semester. So if you do want to see the details will be there. You'll also hopefully have some motivation to take complex analysis in the future. Alright, so now here's the lemma. Poisson lambda 1 plus Poisson lambda 2 is Poisson lambda 1 plus lambda 2. So we actually proved this in the generating function chapter, which I know you've all started to read. So I will just review the argument there. The chapter talks at length about how to look at the algebra and see what's going on. Alright, so now, how do we deal with the sums of two random variables? What do we use? So what tool do I have to deal with the sum of two random variables? Convolutions. This is going to be a little bit different than all the other convolutions we've seen before. What's different between this and the other cases?
Discrete.
Yeah, it's discrete. That's the only difference. So let's let x be x lambda 1 plus x lambda 2. So the probability that x equals m, it's going to be the sum, the probability x lambda 1 equals k times the probability x lambda 2 equals m minus k. And k goes from 0 to infinity. Okay? So this is just the discrete form of the integral. And so if I want the sum to equal m, well, this has to take on some value, call it k. And if the sum has to be m, then this has to be m minus k. So what's the range of k, since we're doing Poisson random variables? Does k really go from 0 to infinity? Can I truncate the sum a little bit? Yes.
From 0 to m.
It goes from 0 to m. Because once k exceeds m, the probability is 0. So, think of a Poisson as telling you, how many accents you have at a given intersection. That's one of the standard places where Poisson occurs. You're not going to have negative accidents at an intersection. Cars are not going to emerge repaired, from all the fender benders they've had in their past. Okay, that is not going to happen. There is 0 probability. So for this one, because it's Poisson, I can replace the infinity with m. And now all we have to do is do algebra. And sometimes it's kind of soothing. Probability x lambda 1 equals k, lambda 1 to the k e to the minus lambda 1 over k factorial, lambda 2 to the m minus k e to the minus lambda 2 over m minus k factorial. And at this point, you're essentially detectives. You're trying to see, does this look like anything you've seen before? Are there any algebraic steps that are kind of obvious that you want to do? So we've got a sum over k. Anything you want to do with the things in the sum? Yeah. What's the first algebraic simplification I could try to do? Yeah.
Pull out e to the minus lambda 1.
Yeah, pull out e to the minus lambda 1, e to the minus lambda 2. And so I would get e to the minus, I'm going to write it as lambda 1 plus lambda 2. Because again, I have some intuition that it's Poisson. If we were meeting, 5 days a week, we would have done some numerical simulations, we would have added them together, and you would have seen the data that it's looking Poisson. Bless you. In the interest of time, I would just say you've just imagined you've done that. Okay? Now what are we left with? We're left with the sum. K goes from 0 to m. There's lots of ways to write this. I'll write it as 1 over k factorial, 1 over m minus k factorial, lambda 1 to the k, lambda 2 to the m minus k. What is that looking a lot like? That should remind you of something. When you see the denominator k factorial m minus k factorial, what's that looking like?
Binomial coefficient.
Like binomial coefficient. What's it missing to make it a binomial coefficient? What am I missing?
I forget what it is.
Yes.
N factorial.
An m factorial on the top. So can I just put in an m factorial on the top? No. What can I do? I can multiply by 1. Right? I can't do that much. I can multiply by 1, I can add 0, and I can take logarithms. And we'll see if I can do all three, the Holy Trinity today. I multiply by m factorial, and I have to divide by m factorial outside. Okay? That's fine. This is really beginning to look a lot like a Poisson, right? And now I have a sum. K goes from 0 to m of m choose k, lambda 1 to the m, lambda 1 to the k, lambda 2 to the m minus k. What do I use to simplify this expression here? So where have we seen that expression before? Yes?
Well, I mean, that also looks like a binomial.
It is, yep. So this becomes what?
Lambda 1 plus lambda 2 to that.
Right, and if we're trying to get a Poisson, what are we missing? We're missing the lambda 1 plus lambda 2 to the m. So if you have the intuition that it's a Poisson, then you should be guessing, this has to somehow become lambda 1 plus lambda 2 to the m. Oh, good, that's the binomial thing. Hey, right, lambda 1 plus lambda 2 to the m, e to the minus m over m factorial. And that finishes the proof. So Poisson plus Poisson is Poisson. Okay? And again, I strongly urge you, write some Mathematica code and take some Poissons and add them together. And just see what goes on. and look at the distribution and see that Poisson plus Poisson really is Poisson. Okay, any questions on Poisson plus Poisson? Okay, so now we're going to use the central limit theorem. I'm going to erase the central limit theorem. You've all memorized the central limit theorem by now. And in this way we'll have plenty of space for the calculation. So we're going to now prove that the central limit theorem implies Stirling's formula. So xi will be Poisson with parameter 1. x1 plus xn will be Poisson with parameter n. Alright, and let's give this variable name. Let's call this variable x. So x will be the sum of n independent, identically distributed Poisson-random variables with parameter 1. So x is Poisson with parameter n. Alright, so the probability that x equals m is what? What's the parameter, the Poisson parameter for this? N. So we're going to get n to the m, e to the minus n, divided by m factorial. Right? I'm just taking the Poisson random variable, and wherever I see lambda, I'm replacing lambda with n. This is true for all values of m. Is there a particularly useful value of m to take to make this look a lot like this? N, right? Try n equals n. And so now we get the probability that x equals n is n to the n, e to the minus n, divided by n factorial. That's exactly what we're going for. Okay, so all we have to do now is use the central limit theorem. Okay. So, the central limit theorem says the sum of Poissons is going to converge to being normally distributed, and we know exactly what normal it is. What's the mean of x? So again, x is x1 plus xn. The expected value of x is what? So what's the expected value of x?
N.
N. And what's its variance? Alright, that's a little bit harder. We need to remember what's the variance for Poisson. So is the variance of a Poisson with parameter lambda, is it equal to lambda? What is it, 2 lambda? What is it? I'm sorry? Alright, so let's calculate the expected value of x1 squared. So we need to calculate, what is the standard deviation, what is the variance of individual Poisson. So we would want to sum k goes from 0 to infinity of k squared, and then we have lambda is just 1, right? So we get 1 to the k e to the minus 1 over k factorial. Right? And so then the question is, what is this sum equal? And so there's lots of different ways of doing this. We talked about doing it by differentiating identities. If k equals 0, we're fine. The contribution is just 0. So we can start the sum at k equals 1. K goes from 1 to infinity, and we have k e to the minus 1, and then k divided by k is k minus 1 factorial. Right? Instead of having a k, I'd rather have a k minus 1. So let's just write this as a sum. K goes from 1 to infinity of k minus 1 plus 1 e to the minus 1 over k minus 1 factorial. What have I done?
I've added 0.
Right? The trifecta, the triple crown, right? We did it all today. This is why I'm not doing differentiating identities. This way I get to add 0. Right? It's a really good day. It's not even 11 o'clock. So the k minus 1 over k minus 1, well, I can cancel that as long as k is at least 2. When k equals 1, do I really worry about a k minus 1 term? No, because k minus 1 will just be 0. So this is the same as the sum, k goes from 2 to infinity, e to the minus 1 over k minus 2 factorial, plus the sum, k goes from 1 to infinity, e to the minus 1 over k minus 1 factorial. What does this sum equal? I can pull out the e to the minus 1, and what do I get? So if I pull out the e to the minus 1, I have a sum, k goes from 2 to infinity, of 1 over k minus 2 factorial. But if I shift my index, I've got 1 over 0 factorial, plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial. What's this number? E. And the next one, I pull out an e to the minus 1, I have a sum, k goes from 1 to infinity, 1 over k minus 1 factorial. What does that equal? I'm sorry? That's also equal to e. So I get e inverse times z plus e inverse times z is 2. So the expected value of x1 squared is 2. So the variance of x1 is the expected value of x1 squared minus the expected value of x1 squared. So I get 2 minus 1 or 1. Okay? This is one reason why you want to memorize means and standard deviations of your friends. Okay? So that you don't have to do this. What could somebody have done to save us some time? Looked it up. Looked it up in your notes, go to Wikipedia. You know, this is the era of cell phones. And quickly look up these facts. But it's nice to be able to rederive them and see how to do this. As we've talked in the past about how to do algebra like this. You can also do this by doing generating functions. You can also do this, which we'll talk about in a week or so. You can also do this using differentiating identities. And what's nice about the differentiating identities approach is you do it for all lambda simultaneously. We would now, if I gave you a Poisson with parameter 3, I'd have to do it all over again. Well, no, I can sneak it in because a Poisson with parameter 3 is the same as the sum of 3 Poissons with parameter 1. And so I can sneak in and get it that way. All right. Questions about the calculation? So we now know that the variance of x1 is 1. We have n of them, so what's the variance? Variance is just n. Okay? So now we're going to use the central limit theorem. So we know exactly what the probability that x equals n is. So the probability that x equals n is n to the n, e to the minus n, over square root of 2 pi n. And now, according to the central limit theorem, x is approximately normally distributed. So if I give you a continuous random variable, question? Oh, sorry.
Yeah.
N factorial. I just have root 2 pi n on my mind because it's coming in very, very soon. It's on hot standby right now. And it jumped the gun a bit. I apologize. What is the probability a continuous random variable takes on the value n? Good guess. No. What's the probability a continuous random variable takes on the value n?
0.
0. The value 5. I'm sorry?
Correct.
Yeah. No matter what number I give you, the probability is 0. Okay. So this converges to being normally distributed, and the probability of taking on the value n is 0. That doesn't seem to be good. What I really need to do is I want to approximate this. But remember, the Poisson is discrete. So what I have over here is I have n. Here's my normal. and I really go from n plus a half to n minus a half. And I say all the area under the curve from n minus a half to n plus a half is going to be the probability that I'm n. Because really, I can interpret this as the probability that n minus a half is less than equal to x is less than equal to n plus a half. And that's a much more reasonable interpretation to do. And that's what I'm going to try to approximate with the normal. So this should be equal to the integral from n minus a half to n plus a half, 1 over, what do I put in now? Now the square root of 2 pi n comes in, right? Because I have my Gaussian, 2 pi n e to the minus x minus n squared over 2n. Why? Because it's a mean of n, and it's a variance of n. Okay? So let's look at this integral. N goes from minus a half to, I'm sorry, the integration goes from n minus a half to n plus a half. So I can write x as maybe n plus t. And so this would be 1 over square root of 2 pi n, the integral from minus a half to a half of e to the minus t squared over 2n dt. Right? Now I've just changed variables. I've just let x equal n plus t. Why? Look, x goes from n minus a half to n plus a half. X is living near n. So if x is living near n, why don't I write x as n plus something? And the t moves only a very small amount. What can you tell me about e to the negative t squared over 2n if n is big? What does it look like?
0.
What looks like 0?
The exponent.
The exponent looks like 0, right? There's very little change in this. You think of n as huge, t is going from minus a half to plus a half. This is essentially e to the negative 1 over 2n. It's essentially e raised to the 0th power, and e to the 0 is 1. So how would you approximate that integral? So I'm integrating a function which is approximately 1 from minus a half to a half. What's the length of the interval? 1. And the function is approximately 1. So the integral is 1. So we get n to the n, e to the minus n, over n factorial is approximately 1 over square root of 2 pi n. Or n to the n, e to the minus n, square root of 2 pi n is approximately n factorial. That's a really nice way to attack Stirling. Could we do better? Could we get upper and lower bounds? How could we get an upper bound for this integral? So where's this integral largest? What value of t? So what value of t makes the integration as large as possible? It's either going to be 0, a half, or minus a half. You've got 3 choices, right? By symmetry, it's not going to be anything else. You've got a 1 in 3 chance of being right, or a 1 in 2 chance, because minus a half and a half should be the same. Right? So you've really got a 50-50 chance. You're not going to get much better deals in life than that. 0? 0. So if we put in 0, we get e to the 0, which is 1. If t is a little bit away from 0, we have e to a negative power. That's 1 over a little bit of e. It's a little bit less than 1. So we can upper bound this integral with 1. What would be a lower bound for this integral? Lower bound would be minus a half, or a half. So if we put in t equals a half, that's the smallest thing would be. And that would give us an e to the negative 1 over 8n. So we can actually do a lot of work. We can actually get better estimates for this integral. We can actually get the next few terms in the Taylor series expansion. We could actually expand this out and integrate term by term. The exponential series converges very well. So if you wanted to actually get some additional terms in Stirling, you can do that. There's one small thing we've glossed over. And I've written an equal sign over here. This is really not an equal sign. This is an approximately equal sign. The central limit theorem says that this is approximately equal to the area under the Gaussian. So one of the things you want to know is, okay, the central limit theorem, great, it converges to being normally distributed. How much is it missing by? How close is it? Can you quantify the error? And so, in some cases, we are able to quantify the error. There is a 10 to 25% chance that there may be a class next year at Williams where we talk about how would you do advanced probability and quantify things like this. How close is it? For a lot of purposes, we don't really care that much. We know it converges, and for the most part, we just cross our fingers and hope. How many of you have taken a stats class? How big must n be before you're usually safe?
10% of the population.
I think that's a different problem. How many summons do you need before the sum can be pretty well approximated by the normal?
Like 100, 200. No, they're like 40.
I was taught around 25 to 30. I mean, there has been some inflation since I was a young scholar. Typically they say, once you're around 25 or 30, that's more than enough n for this to be pretty close. And it's going to be a pretty good approximation. But again, if you're proving a math theorem, you want more than a pretty good approximation. There's one other way to attack Stirling's formula. I'm not going to go through it. It's in section 18.6 of the book. It uses a method called stationary phase, which is a very powerful tool to try to figure out approximately how big is n factorial. We're at this sweet spot right now where I don't have enough time to do Stirling and central limit theorem, and I don't really have enough time to start generating functions. So what I'll do, yes. Oh, good, I'll answer questions, yes.
Can you just sort of quickly recap where we started on this?
Sure, so what we did is we started by saying, let's consider the case of n independent identically distributed Poisson random variables with parameter 1.
Right.
And we proved that the sum of Poisson is Poisson.
Right.
So this is going to be Poisson with parameter n. So if I want to know what's the probability that x takes on a value m, it's just going to be n to the m e to the minus n over m factorial. Because really, my parameter lambda equals n.
Right.
So we know exactly what the probability is that this sum takes on a given value. And so if I want to know the probability it takes on the value n, it's just n to the n e to the minus n over n factorial. But we know that sums of independent identically distributed random variables should be converging to normally distributed. And so this sum should be a normal with mean n and variance n. And so now we just have to integrate the normal. And the difficulty, this is the most common mistake people make, is this is a discrete random variable. So I can't really compare the probability that it takes on the value n to the value that the normal takes on the value n. In Friday's class, we're going to look at flipping coins and proving the central limit theorem in the case of flipping coins by using Stirling's formula. And when you flip coins, we're going to have a head worth 1 and a tail worth minus 1. So if I flip an even number of times, what are the possible outcomes for number of heads plus the net number of heads and tails? So every head is a plus 1, every tail is a minus 1. I flip an even number of times. Which numbers can I see, which numbers can I not see? So what kind of outcomes can I get? I flip an even number of times.
So you expect
Even.
to get 0.
I expect to get 0. What else could I get?
Even numbers.
Even numbers. I can't get any odd numbers. If I flip a fair coin or even a biased coin an even number of times, and every head is a plus 1 and every tail is a minus 1, I'm never going to have a negative, I'm never going to have an odd number. So when I'm trying to then do my comparisons, we're going to have this annoying factor too that we're going to have to just shove in. If you've ever done like a physics or chemistry, Alright, so we have I think 1 minute left, and I do want to talk very briefly about section 18.6. So 18.6 uses the method of stationary phase. And all I want to say about this is we use gamma of s is the integral from 0 to infinity of e to the minus x to the s minus 1 dx. And the reason I wanted to mention this is to show you one of the reasons why we care about the gamma function. I've replaced the factorial with an integral of a really nice function. And now I have the possibility of using techniques from analysis to approximate this integral. And if I can approximate this integral, I can then approximate n factorial. Because we have the annoyance, gamma of n plus 1 is n factorial, shifted over. Okay, so this is a good place to start. The review dinner will be sometime between 5:30 and 6:30 is when we'll start. It's a function of how long I should probably turn it off here.